Okay, calculus students, today we are going to switch the vocabulary of what we were talking about today with the definition of a tangent line, and we're going to turn that over into the derivative of a function. But as many of you are already aware, or that you will see right now, there is very little, if anything, that is different in the mathematical computations. So let's take a look. Our objective for the day is we're going to use the definition of a tangent line in order to find derivatives of functions. Okay, we're going to demonstrate the ability to use the limit process in order to find the derivatives of functions. And the essential question for you to self-reflect upon the end of your practice assignment would be, can I apply the limit process in order to find the derivative of a function? Okay. Now we started this discussion by looking at the tangent line problem. Okay. The use of a limit to define a tangent line opens up one of the three fundamental topics of calculus, which is the idea of differentiation. Okay. Now, the derivative of a function f at any location in the domain x is given by this expression. Now, you should very much recognize the right side of this equation. That would be the definition of a tangent line that we discovered today. Now, new notation there. Okay, f prime of x is equal to the limit as x approaches 0 of f of x plus delta x minus f of x divided by delta x. Okay, so after the discussion today and then the questions on the assignment should be well familiar with that formula. Well, it's being redefined as a derivative, and that is, of course, provided that the limit actually exists. So the act of finding a derivative of a function is called differentiation. And there are a couple of prototypical notations for derivatives, and those notations look like this. Here's kind of the most common. As you saw up above, we've got that little apostrophe looking guy, which we call prime in mathematics. So we have f prime of x, and that is how it is pronounced. And then we run into this one a great deal in calculus, and that is dy over dx, and it is pronounced the derivative of y with respect to x. Okay, so let's take a look at an example here. Okay, as we already stated, we're kind of already basically just renaming this procedure. It is the same mathematics that we had before, just kind of a new application, or basically a new naming system, for lack of a better way of putting it. Okay, so let's take a look at an example. Here we have a function x cubed plus 2x. We are instructed to find the derivative by the limit process. Okay, well, it's the same definition. Okay, the definition of a tangent line and the limit process. Okay, we're looking at f prime of x is equal to the limit as x approaches 0 of the same ratio that we were looking at earlier. Okay, so applying that rule to the function that we have, of course, in the numerator of the fraction there, the ratio there, we're going to take the function and evaluate it at x plus delta x. From that evaluation, we will subtract the function itself, and that will remain over delta x. So plugging this information in, we have basically this. Now, obviously, the algebra is going to go a little crazy there for a moment because we have a binomial being cubed, and then you've got some distribution going on for the second two binomials. So we're going to pick up a whole bunch of terms here. Okay, now I have done all of the terms and simply recorded them instead of writing them all down and showing all my work, which is a no-no. I shouldn't have done that, but I did it anyway. Okay, so what we're going to have now is a situation where a lot of stuff is going to cancel. So we're going to be looking for like terms to see what will join together. Okay, and in the end, what we're going to end up is there were 3 x squared delta x's, 3x delta x squareds, 3 delta x's, okay, delta x cubed, and then a pair of delta x's, all over delta x. Now, obviously, the thing that we're watching out for after that expansion and then the simplification is the possibility that we may be able to cancel out a delta x so that the limit may help us out of a little bit of a jam here. Okay, so factoring out a delta x in the numerator, all of the terms in that polynomial had a delta x that they could get rid of. So I've taken it away from all of those terms, and then it is able to cancel with the delta x that is in the denominator. Now we are out of the woods as far as the limit. When delta x was going to try to go to 0, now that does not mess with our denominator anymore, so we are free to evaluate the limit and see what happens. Now, of course, sending delta x to 0 is going to knock out those two central terms inside of the polynomial, and we are left with an expression of 3x squared plus 2. Okay, so now this would be a situation where this is what I messed up in class today. If we had a value x that we wanted to find out what is going on with the slope, we would plug in that value x that would translate into information about the slope, and then we would then be free to try to figure out what's going on with the tangent line. Okay. So let's take it one step further on a next example. Use the derivative to find the slope of the function f prime of x for f of x equals the square root of x. And we're going to evaluate at 1 in the domain. Okay. Well, we're using the limit definition here, or the definition of the tangent line. Okay, so we're going to evaluate the function at x plus delta x, then subtract the function itself, and then it is, of course, over delta x. Okay, well, this generates a little bit of a problem here for us at the moment. Okay, we have the square root of x plus delta x. Now, this is a term that we are pretty much entirely unfamiliar with, and clearly we're not going to be able to just factor out from underneath that radical anything that's being added or subtracted, let alone x plus delta x. Okay, so we better come up with an alternate strategy on what we can do to try to attempt to simplify such a problem. And one of the strategies that we employ whenever we run into a binomial that we basically do not know what to do with, and that's what we're looking at here in the numerator. We have these two radicals that are being subtracted from each other. They are not like terms, so they can't be combined, and we do not seem to have any strategy as far as simplifying either one of them. So we do what we call rationalizing the binomial. Okay, well, in this case, the binomial is in the numerator, so we're going to try to rationalize the numerator. And the way that we rationalize it is we hit the term, or the whatever it is, in this case the numerator, we hit it with its conjugate. Okay, so if we have a square root of x plus delta x minus the square root of x, one of the strategies we can employ is to multiply it by the exact same binomial, only the conjugate, so change the sign in between them, square root of x plus delta x plus the square root of x. And of course, whatever you do to the numerator of a fraction, you must also do to the denominator. And so essentially what we are doing here is we are multiplying that fraction by 1. Okay, now doing the distribution through that. Okay, now after the distribution is done, here is what we end up with. The numerator is greatly simplified, which is what we were actually hoping for. Now the denominator got really pretty ugly there. Okay, but what we do find is that we have a situation where we have delta x kind of prevalent there in the denominator. And if we look a little closer at the numerator simplifies down even one step forward. We have 1x to the first, and we have a negative 1x to the first. Okay, so those actually cancel, and then we are left with a monomial of a numerator, and the only term it is delta x. Okay, so we have found a situation where, once again, the delta x's can cancel from numerator to denominator. And in so doing, we have caused ourselves a situation where it looks like we'll be able to send the limit at delta x, we can send it to 0, and that will not affect the denominator in such a way, because now we don't have that delta x isn't the only thing in the denominator. Sending delta x to 0 is actually going to be an allowable thing that's not going to cause problems. So what we have is we have a square root of x and then another square root of x in the denominator, so obviously we have two square roots of x in the denominator. Okay, so there's an expression there dealing with this. Okay, so the limit process is complete. We now have an expression that can deal with the, or evaluate at any particular value we want in the domain. Okay, so let's see if I've got my notes right on this one. Okay, we're going to be evaluating at 1 in the domain. Okay, so in order to do that, all right, we're going to plug in our, remove any x's that we have and plug in 1 instead. So yes, I actually did get this one correct, did better than yesterday. Okay, and simplifying down, we have a slope expression there at 1 in the domain. Our slope of our line tangent is 1/2. Okay, and we could have applied this to any particular location they wanted. Okay, so if we were looking at 0 in the domain, okay, well, obviously that causes a square root of 0 in the denominator. That is going to 0 the denominator out, and that's a situation we should understand. What does that mean? Your slope fraction just went to 0 in the denominator. Okay, that means our curve is basically at that moment becoming vertical, so that means our tangent line is moving vertical as well. Slope is undefined, and we'd have to respond with something like infinity if we were talking about a slope fraction. Okay, so just a handful of questions on the assignment. We're looking at page 103, numbers 14, 15, 20, 21, and 24. Should just be more practice getting this skill under our belt before we move forward.